Welcome to MyProjectBazaar.com. Now we discuss about the product for overcoming computational errors in sensing platform through embedded machine learning kernels. Next we see the abstract for the product. Powerful algorithms have emerged from the domain of machine learning that enable data-driven methods for modeling and analyzing application signals. The strength of machine learning is that it enables the creation of high-order models from previously observed data. This is the valuable to embedded sensing application for two reasons. It enables to analyze modeling that are all well suited for classification, recognition and mining functions, which are the becoming increasingly prominent, and it overcomes if needed to analytical model which are often invisible for a physically complex enabled signal of interest. The focus of this paper is to extend the potential benefits of machine learning beyond enabling analysis model for application signal to mitigating the need for designing merging against a significant class of hardware fault, namely static fault. Example for open shorts caused by lithographic defect, logical gate static noise margin, violation caused by the transistor variability, and so on. They imposed substantial cost on system resources, area, energy, or so on, and due to the need for designing merging, while such the fault can be impossible to predict, the manifest as the serve complex and highly transient error, which shows the machine learning methods to enable the constructive analytical model is present to resulting errors overcoming the impact of static fault. We describe the architecture that utilize the principle towards system level resilience, little overhead in terms of energy and hardware approach to refer to the data driven hardware resilience architecture. B presents the approach for overcoming computational error in runtime and originate from the static hardware fault in digital processor. This approach based embedded machine learning stages that learn and model the statistics of the computational output in the presence of error and resulting the error aware model to embedded analysis. We analyze the hardware system to analyze the sensor data of ECG based sizer detection, ECG based cardiac arrhythmia detector. This system to small kernel for fault-free hardware to construct and apply the error-aware model. This system constructs the own error-aware models with minimal overhead through the use of embedded active learning framework. Via the field programmable gate array implementation of hardware experimentals stacked the fault are injected at controllable rate within the synthesized gate level netlist to permit characterization. Sizer detector demonstrate restored performance of depth fault for overall architecture. This is our flow diagram for the product. First we select any one of the given input ECG signal to be browsed. Then to apply the filtering function. This filtering function to filter the given selected input ECG signal and to apply the low pass filter for using the filtering function, and to write all the values to the text format, because Xilinx only used into the integer values, so we write all the values to the text. These functions to be presented in MATLAB 2013 A software, and to apply the MATLAB file to Xilinx software and to call the Xilinx software directly, and to identify the QRS deduction based DFT feature extraction architecture. This DFT feature extraction is mainly used to the approximate multiplier functions, and to identify the Gaussian kernel unit using the approximate multiplier. The approximate multiplier to identify the DFT feature extraction and the approximate multiplication function, then to pass the Cardiac and exponential architecture. The Cardiac based exponential based architecture is used to identify the exponential processing element using the Cardiac architecture. The Cardiac architecture to reduce the number of rotating function in our exponential processing element architecture. The kernel identification unit is used to identify the minimum distance value for overall test vector and support vector values. Then to passing the scaling unit function. The scaling unit function is used to identify the overall data-based support vector and pre-processing for all the support vectors, and to set the any threshold value, to set the minimum threshold value for the given input vectors and the test vectors. Then the test vector and the given input support vectors to be compared with minimum threshold values, and to identify the satisfy the condition to be yes and the not satisfied condition to be no. The not satisfied to be analyzes the another one data. If the condition is satisfied, to passing the this data to be label. The label to be identify the which type of disease to be presented in overall input ECG signal based on our QEC detection process, and to identify the QEC detection process and compared with the overall database, and to finally life threatening result for our required simulation window. These functions are all the present to be Xilinx 14.2 software. This is the final process for our overall architecture. We use the approximate multiplier for these three functions also. Finally, we see the output for the product. First, we run the main function to be run and select the any one of the ECG signal for overall dataset. We select the one of the dataset and to select selected signal to be displayed, and to limited signal to be generated. This is the selected limited ECG signal without noise. We apply the low pass filter and remove the noise, and to write all the values to the text, and to apply the input for the Xilinx software, because Xilinx software consists the only integer value to be presented. So the inputs are presented from the MATLAB and to process the our overall architecture. Then to simulation window and to simulate this simulate model. The simulate BGL model to be separate presented the overall simulation process. This simulation process after completed the simulation window to generate the iSim project navigator file. This navigator file is used to represent the simulation purpose. This is the given ECG dataset for overall architecture signal. Run all the data and to finally generate the output data status, ECG data status. Then to apply the clocking signal and to create this signal level to be analyzed. And finally, we classify the which type of the signal life threatening arrhythmia type is calculator. Then to apply the one and run. And finally, we identify the signal level. Arrhythmia is a bradycardia or apticardia or the normal signal. So the signal to be normal, to be identify the final classification process. This is the classification process output for overall architecture. This is the final output for the product.